Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem minimum falling path sum 2. I would actually say this problem is slightly easier than yesterday's problem. So whether you want to say this is a medium problem or yesterday's problem is actually a hard problem, well, that's up to you. But this one is slightly easier in my humble opinion. The general idea is pretty simple. We're given a two-dimensional grid, and this is actually going to be a square grid. I guess that's a little bit convenient for us, but it doesn't really make a difference whether it would be like not square. The idea is we want to create a path starting from the top going to the bottom. And we can start anywhere, either here or here or here. We can start in any position in the first row. But the problem is now when we go to the second row, we can pick any value, but we can't pick the value that's in the same column as the previous value. Basically, two consecutive rows cannot have the same column chosen. That's the rule. That's the only rule. So given that, we want to find the path that minimizes the total sum and then return whatever that total sum happens to be. So here we find that the path is going to be 1, 5, 7, and the total sum is going to be 13. Of course, a smaller sum would have been 1, 4, 7, but you can see why that's not allowed because it's adjacent to these two. Not super crazy complex, right? When you think about it, the problem isn't super different from yesterday's problem, right? The idea is that we have a bunch of choices. In this case, though, we don't just have two choices. Well, in this problem, we kind of do because we can't pick this, so then we have two choices remaining. But you can imagine that we have a larger grid, maybe it's a 5 by 5 grid. In that case, the idea would be, this is really poorly drawn, but I hope you get the idea. The idea would be that if we have chosen this value, then for the next choice that we make, we can choose this value, but not this one, and we can choose this one and this one. So in terms of what our brute force solution would look like, we're going to do this recursively because this problem really lends itself to making different decisions, as we kind of just went over. Going back to the simple case, the idea is if we first choose 1, or maybe we first choose 2, or maybe we first choose 3. Those are the choices that we initially have in the first row. But after we make a choice, well then, for 1, we can either choose 5 or 6. We can't choose 4. For 2, we can either choose 4 or 6. For 3, we can either choose 4 or 5. I won't spend too much time on this recursive solution because I want to spend more time on the non-recursive solutions, but I still think it's worth going over this, especially if you're a beginner, because the recursive solution is usually a lot easier and it helps you build intuition to solve the problem more efficiently. So this is the idea. We could continue drawing this recursive tree, and I would recommend you to do so if you're not super familiar with this. And basically, we would choose the path that is going to minimize the total. If we were to go through every single path, like from here, etc., we would find that this path would be the one that would minimize the result. And that's what we would return. The problem here is, as you can kind of tell, this is not very efficient. I think it's going to be n to the power of n because that's how many branches we'll have in the worst case. That's what the height of this is going to be. Good thing is we can implement caching to cut down on a lot of the repeated work. As you can see here, is a subproblem. This is the original problem we're trying to solve, starting from the beginning. But here is a subproblem. Here, what we're actually asking is, what's the minimum path starting from 5? Well, 5 is a value. It could be duplicated in other parts of the grid. What really defines this cell is the coordinates of that cell, aka the row column pair. That's what tells us that this subproblem over here, which the result of that subproblem, what's the minimum path from here? It'd be 5 plus 7. The result of that subproblem is going to be the exact same as the result of this subproblem, which has been shown up over here because that's the exact same cell. So if we were to do that, we would find that we don't need this, or this. We don't need to expand the tree in any of those spots because they've already shown up over here. So with that idea, we're going to implement caching, a memoization technique, and I'll go over the overall time complexity in the code for this recursive solution. So I'm going to first just get the dimension of the grid. Usually I do this by getting the number of rows and columns, but in this case, we know that that's going to be the same. Then I'm going to create a helper function. We only need to keep track of the coordinates that we are currently at. And in this recursive function, I didn't really talk about the base case, but the base case could either be when the row has gone out of bounds, when it's equal to n, or it could be when it's n minus 1, meaning we've reached the last row. If that's the case, well, in the last row, we only have one value. We don't have any additional choices to make at that point. So what we can do is return the value at that grid. It's in the last row. So this is kind of the base case for that. Otherwise, we do have more decisions to make. We are ultimately trying to find the result from this coordinate. What's the minimum path that we could get? And since we're trying to minimize it, we shouldn't set this to 0. We should set this to a really big number. In my case, in Python, I like to do infinity. And we know this is what we're ultimately going to return. Now, how do we minimize it? Well, we're at this column and this row. So we want to choose from every single column, and I'm going to call that the next column. So for the next column in range n, we want to choose that from the next row. The only problem is that if we do this, like if we say, okay, the result is going to be equal to the minimum of either itself or the current value, grid at the current row plus column, plus the solution to the subproblem. What's the subproblem? It's going to be helper of row plus 1, the next row, of course. That's never going to be anything different. And next column, we're getting this from just iterating over here. The only problem with doing it like this is what if next column is the same as the current column? So the only thing we need to do before we try to execute this is just make sure that they're not the same. Make sure column is not equal to next column. If that's the case, go ahead and execute this part of the code. And after we've done all of this, this is the recursive solution. We haven't added caching yet, but I haven't actually finished the solution. So let me go ahead and do that down here. This helper function, where do we call it from? We call helper from the first row, of course, row 0. But what about which column do we call it from? We don't really know. We have to try every possible way. So in order to do that, we're going to say for column in range n, and I'm going to call the helper from every single starting column. And once again, we're trying to minimize the result. So I'm going to initialize the result over here to infinity, and I'm going to set it to the minimum of itself as well as the result of the recursive call. And then after that, we return this. So this is the brute force solution, the really inefficient solution. We can add caching to this to definitely improve the time complexity. So I'm going to create a hash map up here. That's the cache. And in here, I'm going to check, is this subproblem already solved? Is this key already in the cache? If it is, let's return the solution that we already stored in there. And if it's not already stored, let's compute it. And then before we return down there, let's go ahead and very quickly cache the result. So cache over here of this subproblem is going to be equal to a result, and then we return it. This is the recursive solution. But on the left, you can see when I try to execute it, it does get time limit exceeded. Let's analyze the time complexity of this solution. So it looks like, how many unique times is this function going to be called? I always like to start with that. When we have a recursive function that we are using caching with, the maximum number of times it could be called is the maximum number of combinations of the inputs. The number of possible different values for row is, of course, going to be n. Same with the column. So the number of times this function could be called, and it's going to actually be fully executed, not just returned like this, is going to be n squared, right? So n squared. And what is the time it would take to actually execute this entire function once? Well, that's defined by this loop. If we didn't have the loop, this would just be an O of 1 thing. But since we do have the loop, then we're adding n again. We're multiplying this by n. Therefore, the overall time complexity is n cubed. The overall memory complexity is defined by this cache, which is going to be O of n squared. So that's the space complexity. Let me show you the first bottom-up solution to this problem that doesn't require recursion. And then I'm going to show you in the third solution how to fully optimize it. So the idea with the bottom-up solution is very similar to the recursive solution. That's why I always like to start with the recursive solution. When we reach the base case, do you kind of notice what happens? From here, what's the minimum path going downwards? Of course, it's just 7, right? From here, what's the minimum path? It's just 8. From here, it's just 9. Okay, that's the base case. Now, when we get to the next level, we're going to kind of do the same thing. We're trying to figure out what's the minimum path from 4. Well, in order to do that, we have to iterate over the entire bottom row. We have to skip this value, but then we have to look at 8 and say, okay, 8 plus 4 is 12. So then the minimum from here is going to be 12. And then we're going to try 9. The original value here was 4, remember? So 4 plus 9 is 13. Is that smaller than 12? Nope. So then we find that the minimum value from here, and let me actually draw a second square to make this even more clear. Here is going to be 12, and then here the values are going to stay the same. And then I could do the same thing for 5. So with 5, we have 2 choices. We have 7 and we have 9. The minimum is of course going to be 5 plus 7, and that's going to be 12 here. From here, we could do the exact same thing. I think we'd get 13. And you could do it this way, this bottom up way. But the only problem with this is you can see our row, we'd have to do the bottom row, and then we'd have to do this row, and then we'd do the first row. And so this is actually how I prefer to do it, but you can see that this would require us creating a loop where our row would have to go in reverse order. For some reason, people prefer to do it the other way, even though it's kind of very different from the recursive solution. People prefer to iterate from the top to the bottom, from left to right or whatever. I don't know why, but that's what people prefer. So that's the solution I'm going to be showing you. The only thing is it requires us to think about the problem slightly differently. Let me show you what I mean. When you think about the problem that they asked us, they said take a path from the top to the bottom, right? That's what they told us. But is that any different than taking a path from the bottom to the top? I don't really think so. How would it be different? The minimum path from the bottom to the top is going to be the same as from the top to the bottom. We can use that to iterate from the top to the bottom. We can actually say that the first row represents the minimum path from here going to the top. And when you think about it like that, it's pretty much the same as I showed you before, except in reverse order. In other words, 1 tells us that this is the path from here to the top. And 2 tells us the minimum path from 2 to the top is just going to be 2. Same thing with 3. And now we use the same logic on the second row. We say, okay, 4, we have 2 choices. We go to 2 or we go to 3. Which one of them minimizes the result? It's obviously this. So we put a 6 over here. For 5, this is our choice and this is our other choice. And then we put a 6 over here. For 6, this is our choice and this is our choice. We put a 7 here. I'll quickly fill out the bottom row because it's not going to take too much time. For 7, we're going to look here and we're going to look here. But this is the interesting part. We're not going to look at the original values. This is our choice, but we want to know how much would the path be from 4 to the top. In other words, the minimum path. And we already computed that over here. That's the power of dynamic programming. We are computing the result of these subproblems so we don't have to do them again. So when we make these 2 choices, we're choosing between 6 and 6. They're the same, so we put a 13 over here. With 8, we're choosing between this, and those real values are 6 and 7. 6 is smaller, so we put a 14 over here. 9, we're choosing between this and this. That's 6 and 6 again, so we'd put 15 over here. Now you probably know what we're going to do, because this represents a path from the bottom to the top, this represents a path from the bottom to the top, and this represents a path from the bottom to the top. We want the minimum among all of these, which is of course going to be 13. That's what we would return. Now, this solution is not an improvement over the previous solution whatsoever, is it? It's definitely not. The time complexity is still going to be big O of n cubed because we're computing the value in every single one of these cells, that's n squared, and to compute the value in a particular cell, we have to loop through the previous row. So that's how this becomes n cubed. And the overall memory complexity obviously is still n squared. Well, this is where the first optimization is going to happen. As you can kind of tell, for us to compute this row, all we needed was the previous row in memory. We didn't need the entire grid in memory. We only needed the previous row. So my claim to you is we can actually solve this problem by keeping at most 2 rows in memory at a time. When we compute the first row, that's great. When we compute the second row, that's also great. But when we try to compute the third row, get rid of this row. We don't even need it in the first place. So I'm going to refer to these rows as DP and next DP. So when we're computing next DP, assume it's empty. Assume that it's filled with infinities, I guess, because we're going to try to minimize the value in each of them. After it's been fully computed, what we're going to do is shift DP down here, get rid of this, and then we're going to try to compute the next row, which again, we're going to call next DP. So this will cut the memory complexity down just to big O of n, because we only have 2 rows in memory at a time. That's 2 times n, which we know reduces to big O of n. Okay, so let me code this up, and then we'll finally get to the last solution, which is the most optimal, and it actually does improve the time complexity as well. So like I said, what I'm going to do is initialize DP, that's our current row, and instead of initializing it to empty, I'm just going to initialize it to the first row, because we know that's what it's going to be anyway. And then we're going to try to compute the values that go in every other row for r in range after the first row. So we say in range from 1 to n. We're going to try to compute next DP. As I mentioned, I'm going to initialize it just to a bunch of infinity values, but it is going to be the same length as the previous row. Okay, so now I'm going to have a pointer for the current column. For this column, we're trying to compute the value that's going to go in next DP for this current column. So we're going to do that for every single column. Now, for us to do that, we have to look at every previous column, right? So I'm going to have a pointer previous column in range n as well. We're going to look at every value in the previous row, and we're going to call that previous column. But we know we are going to skip one. We are going to say, well, if previous column is not equal to current column, that's when we're actually going to look at the value. Remember, what we're trying to compute is next DP at the current column. How do we do it? Well, just as I kind of showed earlier, we want to minimize it. We want to minimize it between whatever it already happens to be and what the current value would be if this is like the candidate that we chose, the previous column. How do we do that? Well, just like I showed earlier, we're going to take the current value in the current column in the current row. So that's just the current value, nothing special here, but we're also going to add to that the value from the previous row, which was DP, from the previous column. So we say DP previous column. Now that I think about it, maybe a better name for this would have been previous DP, and this could have just been regular DP. If that's a change worth making for you, I would recommend you make that if that makes this more clear for you. But the overall math here is going to remain unchanged. The only catch here is every time we go through this entire loop, that means we have fully computed next DP. And after we've done that, let's make sure to set DP equal to next DP. And then, just like I showed, what we return is going to be the minimum value from DP. This is the entire code. Okay, I had a very sloppy mistake. So a grid over here, we're actually going to put the row first. That's generally how we do it. And then the current column. I'm really sorry about that. But otherwise, this is correct. And as you can see on the left, it does actually pass on Leetcode. It's not definitely the most efficient, but it does pass even though the time complexity isn't any different. I think that's just because in this case, we're not using a hash map and we don't have the overhead of recursion. Usually recursion is actually less efficient than just doing it this way. We are saving space though. This is an O of n space solution, but let me show you the fully optimized solution now. If you were clever, going through all of this, you might have noticed something kind of interesting. I guess I'll leave the first row filled in like this. In general, if we were trying to find the minimum path and there were no rules for what we were trying to do, wouldn't we just be greedy? Wouldn't we just take the minimum value from the first row, which is 1? Wouldn't we just take the minimum value from the second row, which is 4, and the minimum value from the third row, which is 7? Well, we know we can't do that because what if those values happen to be in the same column? Well, let me slightly change the problem and then just quickly walk through a little bit of an example. And I kind of want you to actually figure this out on your own. I want to show you it's really nothing crazy when you bring out a pen and paper and just start to try things out and just try to walk through an example. You'll be amazed at what you can notice. Let me just add one more layer to this. And let me just put some random numbers over here. I know this is not a square grid anymore, but that doesn't really matter. It won't really change much. The first row is just going to be filled in by default 1, 2, 3, 4. Okay, now for 4, we have 3 choices. Of course, we can't take 1, which is the minimum value in this row, but now we have 3 choices. What do you think we're going to pick among those values? Of course, the minimum, right? Literally, we're asking what's the minimum of the remaining values among these 3 values? It's 2. Okay, then we put 6 over here. Now with 5, we're skipping this value, but we're asking what's the minimum among these 3 values? Of course, it's going to be 1. So we put a 6 over here. 5 plus 1 is 6. Now from here, skip this. Ask what's the minimum among these 3 values. It's 1. Why would it change, right? Of course, it's going to be 1 for all of these unless we're picking from here. So what are you noticing because of that? From here, what's the minimum? Can't use this. What's the minimum among these 3? It's 1 once again. What are you noticing? Take a second to pause this video if you need to. We only need to keep track of the 2 smallest values among each row. We don't need the whole row. We can go through the row a single time. We don't need to go through the whole row for this value and then go through the whole row for this value and then the same thing for every single value. We don't need to do that. We just need to go through this once, keep track of the 2 smallest values, and then forget about the rest of the others. Because, okay, maybe we can't choose 1 for 4. In that case, we choose the second smallest value. And then for 5, we can't choose this value, but we wouldn't want to anyway. We want the smallest value. So, okay, that works so far. But now what about when we want to compute this row? And let's just assume that like we took this row out of memory because of course we don't need it. When I'm now trying to compute this row with these values, do I really need this entire row in memory? Not only that, do I really need to scan through that whole row for 7 and then scan through that whole row for 8 and then scan through that whole row again and again? Not really. I can just take the 2 smallest values, which are 6 and 6. For this, I can say 7. Well, I can't choose this one, but I can look at this one. That's going to be 13. For this, I can't choose this, but I can choose this one. It's going to be 14. And then I could fill in the rest of these. Now, there's 2 important observations to make with this optimization. Once you realize that you only need to keep track of the 2 smallest values, there's still 2 more observations that we can make. One is that by doing this, we have improved the time complexity from n cubed to n squared. Why is that? Because we only go through each row once, find the 2 smallest, and then we can compute the next row in O of n time. We don't need to go through the entire row for every single value in every single row. So that's one optimization. And the second optimization is we already knew that the space complexity was pretty good. It was big O of n, but actually we've now reduced it to big O of 1. Well, technically big O of 2 because we're keeping 2 values in memory at a time, but that's obviously constant. So this is the time complexity and this is the space complexity of this optimized solution. The only question is, how do we code this up? Like, how do we keep track of the 2 smallest values? Because when we do get the 2 smallest values, not only are we going to need to keep track of what the values were, 6 and 6, but obviously we need to know what the index of those values are as well. Because when we're making the choice, like from here, we have to make sure we don't choose the one that's directly above it. So when we keep track of these, the way I'm going to do it in the code, I'll just give you a sneak peek. Let's say we call it like the 2 smallest. It's going to be an array of tuples, and each tuple is going to be the value and the index pair. So the index is obviously going to be like the column. I guess you could think of it as that. And then the value is going to be the value itself. The reason I'm going to do it this way is because I'd rather not have a million if statements. And I'll show you what I mean when I code it up. It's kind of an opinionated solution though. So if you don't like my solution, you can probably check out somebody else's as well. I like mine because I think it kind of shortens the code a little bit and is relatively readable. So let's get into it. I'm going to show you how I'm going to do this. And it's going to be by implementing a helper function, which is going to get the 2 smallest, get minimum 2. It's going to be given a row and it's going to return the 2 smallest elements. The thing is though, as I said, these 2 smallest are not just going to be an array of values, it's going to be an array of pairs, as I'll kind of outline here. And not only that, but we're going to expect that this row that's given to us is also gonna be a row of pairs in this form. You might be wondering, how would you know to do that? Well, I'll tell you, even as I was writing out the solution, I didn't know to do that either. But later on, when I was coding up the rest of the solution, I quickly realized that it just makes the code a little bit easier, at least the way I was able to implement it. So I'm going to kind of show you the premature optimization, but I'll say that this function is definitely not going to be the common complicated part of this solution. Getting the two smallest values from an array is definitely not the hardest part of this. So what we're going to say is going through the row for value index in row, we're going to try to push the two smallest elements to this array. So what we're going to say is if the length of the two smallest array is less than 2, then just go ahead and push it, and also go ahead and sort the array. You might be wondering, why are we doing this? You'll see in just a second. You might also be wondering, isn't this going to make this inefficient? No, because this array is never going to grow larger than 2. So this is obviously sorting an array of size 2 is not inefficient at all. That's why we can get away with it. The reason I'm doing it is because that makes this code a little bit more readable. So now I'm also going to say, if that's not the case, then we might have to pop a value. But since we know our array is always going to be sorted, let's check the last value in the two smallest array. So that last value will obviously be at index 1. And of that pair, we want to look at the value, which is going to be at index 0. And I'm going to check, is that greater than the current value that we're looking at? Because if it is, then let's go ahead and pop it. Let's go ahead and say to smallest dot pop, and then to smallest append the new value, the new pair, the value index pair. And then after doing that, let's go ahead and sort this. So as you can see, sorting is common to both of these. So I'm going to go ahead and take it out just like this. And then from here, I'm going to go ahead and return to smallest. So nothing super crazy that we're doing in here, but I think it makes the problem a little bit easier. So next, let's go down here and now actually get into the solution. I'm going to get the length of the grid, store it in n. I'm going to get the first row. This is just taking the first row from grid, and I could say grid of 0, but since we want to get the two smallest values from this grid row, like this first row, I'm going to put it into the form that this function will accept. And so we can do that like this in Python, value index for index value in enumerate the grid row at index 0. Now you're starting to kind of see why I prefer using Python. This would be a lot more annoying in another language. Now we're going to say DP is going to be initialized to get the minimum 2 from the first row. So we're just getting the two smallest values from the first row, and we're getting the indexes of them as well. So this is going to be useful for us. Now we're going to go for R in range from 1 to n, similar to the last solution. We're going to try to compute next DP. The only difference is now next DP is going to be empty, and we're going to store it in this form, value index. Now we're going to say for current column in range n, once again, we are trying to compute the minimum path at every single column. The only thing is now it's going to be easier for us to do that. At this current column, the value, which I'm going to store in current value, is the grid at this row at this current column index. And we're trying to compute what's the minimum value for that. And I'm going to store that in a value in a variable here. I'm going to call it minimum value. It's initially going to be set to infinity. And once we find what that minimum value is, we're going to push it to this next DP array. After we do that, you're going to see why I decided to store the values in this form if you haven't already noticed why. Now is the part that might be a little bit confusing because I'm actually going to have another loop. And this is not necessary. You don't have to have a loop. I just personally think it makes the code easier and more readable. So I'm going to loop through the current DP. And we know that the form that that's in is the same form as this. It's in value index form. So I'm going to say previous value, previous column in DP. This seems like it makes the solution less efficient. It seems like it would make it n cubed, but remember that DP is always going to be of length 2, or at most 2. So this is actually not inefficient. Now, what we want to do is minimize the value. So minimum value, we want to set it to the minimum of itself, min value, and what else? The problem is taking the current value, of course, which now we don't need this. We just have the variable for it. So current value. What else? What else do we want to add to this? Well, the solution of the previous subproblem, which is previous val. So we can do it like this. The only problem with this is, you might notice, we aren't making sure that they have different indexes. We're not making sure that current column is different from the previous column. So let's make sure to do that. If current column is different from previous column, that's when we're allowed to execute this code right here. Okay, once we've done that, once we've found the minimum value, what are we going to do? Well, we want to add it to nextDP. So naively, we can say this, nextDP dot append the minimum value. And let's also remember like the index that this minimum value ended at, current column, that's the index. So that's current column. But if we do it this naive way, don't we make it so that nextDP might grow larger than 2? That technically would work, like our solution would still work, but we'd lose the optimization by getting like the 2 minimum values. So we want to keep that optimization. We don't want nextDP to grow larger than 2. So for that reason is why we implemented this helper function up above. So now what we can say is nextDP, set that equal to get minimum 2, passing in nextDP, and this will make sure that it doesn't grow larger than 2. As soon as it hits 3 is when we will pop a value from it. Because let's say this is of length 2, we add 1, make it 3, and then we remove 1 from it. Now, after all of that's done, we can once again update DP to be nextDP, and then after all of that is done, we can return the minimum from DP. Only problem is now DP is no longer just an array of values, but in Python, that's pretty easy to fix. We can convert it to an array of values just like this for val index in DP, and then return the minimum. You might be thinking, by doing this, isn't the memory complexity big O of n? Nope, because DP is never going to be larger than 2 or 3. So we're just creating another array of size 2 or 3. So it's not inefficient at all. This is the entire code. Let's run it to make sure that it works. And as you can see on the left, yes, it does. Now, I do want to mention that this is a very opinionated way of solving the problem. If you want to look at, I guess, the editorial, let's see what they did. The bottom most efficient solution, n squared, O of 1 time. You can see this, in my opinion, monstrosity of a solution. Maybe it's more simple for you. If it is, that's perfectly okay. But I mean, look at how many times they reassign the same exact variable. Even if you remove the comments, I'm pretty sure this would be at least 50 lines of code, whereas my solution is about 28, 30 lines of code. It's up to you if you prefer doing it this way. Feel free. It's probably easier to translate this solution into other languages, I guess. I personally think this is less maintainable. If you found this helpful, check out Leetcode.io. Thanks for watching, and I'll see you soon.